Hey everybody, today we're going to be looking at graphing rationals. So last time we looked at common features of graphs, and we were typically looking at polynomial graphs. For those people who were here last time, you saw some graphs that had some like bell curves and such like that, just to kind of throw you a couple different graphs. But today we're going to be looking at rational graphs. Now, a rational function does some really interesting things. So let's get into it. So today we're going to be looking at those rational graphs. The first step on every problem is going to be factor all parts. So nothing to factor in the top here, but my denominator can factor into x minus 6, x plus 1. Okay, so that being said, first step again is going to be factor. Nothing to factor in the numerator here. My denominator is going to factor into x on this one, x minus 3, x plus 2. Okay. Now again, at this point, I expect that you can factor. So I'm going to be skipping the steps where I'm factoring unless I need to for myself. But for a equals 1, I'm going to be skipping most of those. For the domain restrictions, so remember domain restrictions come from one of two areas for the most part. Either I'm taking the square root of a negative number, which I don't have any square roots here, so not a problem, or I'm dividing by 0. Okay, and there's two places where I could be dividing by 0 here. So x cannot equal 3 or negative 2. I've got problems at negative 3, negative 2. Now hold on to those for a second, because depending on what happens in a little bit, those will either turn into what we call asymptotes or they'll turn into holes. Okay, for intercepts are pretty simple. So for intercepts, what we're going to do, so again, factoring this out, I get x minus 3, x plus 2. So for x-intercepts, I'm going to set y equal to 0. And for y-intercepts, I'm going to set x equal to 0. Okay, now the y-intercepts are super quick. All I'm going to do is set x equal to 0. So I'm going to say 0 minus 1. And it's easier to do on the original function here. That's not always true, but in this case, it definitely is. 0 squared, 0 minus 6. All these zeros just kind of go away. I'm going to be left with negative 1 over negative 6. Or 1 over 6. Okay, so my y-intercept here is going to be 0, 1 over 6. Okay, and then for x-intercepts, this is a little bit more work, but not too bad. So this whole function is going to be 0 if the numerator is 0, because 0 divided by anything other than 0 is going to be 0. 0 divided by 5 is 0. 0 divided by negative 100, still 0. 0 divided by cat, still 0. Okay, it doesn't matter what it is. 0 divided by anything other than 0 is still 0. So as long as the numerator is 0, the whole thing's 0. Okay, well, let's set the numerator equal to 0. Okay, well, in this case, x is going to equal 1. Okay, but I'm asking for an x-intercept. So that's going to be at 1, 0. So let's think about this graphically for a second. Okay, I'm going to put 1 kind of out here just a little bit, and then 2 and 3 and so on. So I have an x-intercept at 1, 0, and then my y-intercept is somewhere on here. Okay, so those are my two intercepts. So again, we have domain restrictions, and we'll talk about what those really mean in a second. And then we have x and y-intercepts here and here. Okay. Now, again, you can only ever have one y-intercept. You can have multiple x-intercepts, and we'll look at a couple later that have that. Okay. So asymptotes. We need to talk about what asymptotes are. I know I've mentioned them before, but what are they really? So let's look at some asymptotes. So I'm going to cheat a little bit here just to give you kind of idea what these things look like, so we know what we're talking about. So let's plug this in. Let's just graph this and see what this looks like. So we're going to do x minus 1. And we always want to use this x, remember, not the one down here. This is always a variable. This may or may not be a variable, depending on who you use the calculator before you. So again, we always want to use the x up here, minus 6. So looking at this graph, okay, whoa, what just happened there? So again, we got this kind of like, what happened? So let's set over Desmos. So, because the one downside to the TI-83s and 84s is they're not always 100% accurate as to what's going on. So let's head over to Desmos and do the same thing. So I'm going to do y equals x minus 1, divided by x squared minus x minus 6. Okay, and this looks a little bit nicer, a little bit clearer as to what's going on. So first off, we notice we do have those two intercepts. Okay. Now, something really weird happens here at -2 and +3. And what's happening there, so x equals -2, and let's make that a dotted line, because that's usually how it is that represent asymptotes. Yeah, let's do that one. Okay, and then also x equals 3. Again, let's make that a dotted line. Okay, so what's happening here is as I get closer and closer and closer to -2, it wants to do something. It wants to be a number, but it can't, because again, we can't divide by -2. Going back to my function, right? I can't have it be -2 and I can't have it be 3. So at those numbers, it gets really, really close to them, but can't quite get there. And as I get closer, it goes off to positive and negative infinity. Well, that's not the only asymptotes I have here. If I look on the ends here, both here, I was using my fingers there, both here and here, it looks like it wants to go to 0. And what we have there is what we call a horizontal asymptote. So let's set that y equals 0. And then we're going to change, we're going to change that as well, because again, it's an asymptote, so we usually distinguish those this way. And then let me make that a color. No, purple's probably going to be the best, unfortunately. So I have this asymptote here, and if I go and I scroll out and I scroll out and scroll out, it's getting closer and closer and closer, and it kind of looks like it's touching, but if I scroll in, not quite. And I can go forever, and it's just never going to quite get there. If I go out even to, 500 or so, if I zoom in enough, and it's going to take a lot at this point, but those aren't quite touching. And again, as I move out, it gets closer and closer and closer, but it never quite gets there. So the way my teacher explained this to me in high school was the super frog principle. Super frog can always jump halfway to where he wants to go. So if I jump halfway from here to a wall, okay, I'm at the halfway point. If I jump halfway again, I'm only at the quarter point, and then the 1/8 point, and then the 1/16, and then the 1/32. So I can jump as many times as I want, but I'm never going to quite get there. There's going to come a point where I'm just so infinitesimally close that it feels like I'm there, but I'm not quite there. So how do we determine an asymptote? Well, there's 3 cases, and we're going to look at the exponents of the leading term. If in this case, we have a 1 there, we're going to call this top term m, and we're going to call the bottom term n. So in this case, m is 1, n is 2. So in this case, n is greater than m. If this is true, then we're always going to have a horizontal, asymptote at y equals 0. Okay, we'll look at cases where that's not the same, but if in the denominator we have a bigger leading exponent, or the degree of it is bigger, then we're always going to have an asymptote at y equals 0. Okay, but hold up a second. We saw some horizontal asymptotes. So let's go back to those horizontal asymptotes. I have problems at 3 and -2. So at 3 and -2, since these do not cancel out, they stay because if nothing cancels out, I'm going to have a horizontal asymptote at x equals 3 and x equals -2. Okay, and I'm using equals here because that's where the asymptotes are at. Okay, so my graph's starting to come together a little bit. Let's think about this. Okay, so I've got an asymptote at, again, if we weren't cheating, if we weren't already knowing what this looks like, I've got an asymptote at -2. I've got a vertical asymptote at 3. I've got an x-intercept here and a y-intercept about right there. Okay, and then I've got a horizontal asymptote at y equals 0. Okay, now if we go back to our graph for a second, we noticed, let's put this back to where it was in the standard. So -10, 10, and then -10 to 10. Close that. If we notice, it seems like the asymptotes, the horizontal asymptotes, only matter on the end. Okay, it doesn't matter in the middle. I can cross in the middle. It's the end that it never quite gets to, and that's going to be important in a minute. So hold on to that for a second. Okay, so the question is, how do we get from this to this? How do we know where the lines go? And that's going to be our sine array. Okay, so sine arrays are the most complicated part. So I have interesting things that happen at x-intercepts and vertical asymptotes. Okay, so at x-intercepts and vertical asymptotes, I'm going to put all of those on my sine array. So I'm going to start off with -2, because that was a vertical asymptote. I'm going to put 1 because that was my x-intercept, and then I'm going to put 3 because that was my my other vertical asymptote. Okay, and then what I'm going to do is for each of these areas, okay, I'm going to use those ideas of, okay, well, what really is going on there? If I'm in -3 land, and let's think about this. So x minus 1, x plus 2, x minus 3. If I'm in this area, okay, the three things that really are mattering here are these: x minus 1, x minus 3, and x minus 2. Or sorry, plus 2. Let's pick a number out here. Again, let's say -3. Okay, that's to the left of the three numbers that I care about. Well, if I put a -3 in for this first term, I'm going to get a negative answer out because -3 minus 1 is negative. Here, I'm also, oops, sorry, I want to have those backwards. I apologize. Same thing though, it would still be negative. Okay, and then this one would also be negative. Okay, picking a number here, let's say something like 0. If I plug a 0 in for this first one, I'm going to get a negative. If I plug a 0 into this one, I'm going to get a negative. If I plug a 0 in here, I'm going to get a positive. And that's true for any number between here. If I do -1.5, I'm still going to get a positive on these and negatives on these. Okay, let's pick 2 here. So I get a negative Okay, but here I'm no longer getting a negative. 2 minus 1 is positive. And then this is positive. Okay, out here, something like 5. 5 minus 3 is going to be positive. And this is also going to be positive, and this is also going to be positive. So you notice I get this nice stair-step pattern. Okay, but what this means is if I'm over here in less than negative 2 land, all my answers are always going to be all negative. Well, a negative times a negative is going to give me a positive, divided by another negative is going to be negative. So this is going to produce a negative result. Negative times a negative is going to be positive, times a positive is going to be positive. Positive, positive gives me a positive, with another negative is going to give me a negative. And then these are all positive. So what this means is my function goes from being negative to positive to negative to positive. So let's go back to that graph that we made. So over here, my graph is negative. So it's somewhere down here. And then we said it was positive all the way up till 1. And then it became negative. And then it was positive again. Well, if I look back at my graph, that's exactly what happens. I'm negative. I hit negative 2, I become positive until 1. I'm negative again, and then I'm positive again. So we can get a nice sketch now because I'm negative. I'm positive until I hit 1, which makes sense because I need to be positive to cross that y-intercept. Then I become negative, and then I'm positive again. So there's a quick sketch of my graph. And again, we're always going to approach these asymptotes, but never quite touch them. Okay, so that's how I would do a sketch of one of these graphs. Okay, and you can always go back, check in your calculator, and make sure you're getting it right. But I'm going to be looking for and making sure that you're getting all these parts. So let's look at another one. Okay, and if we notice here, now they're the same. Okay, that's going to be important in a little bit. But factoring this out, I can take a GCF out of the first. I'm going to be left with x squared minus 1 over x minus 2, x plus 2. This is still factorable. So 2, x minus 1, x plus 1 over x minus 2, x plus 2. So my domain restrictions, again, are coming from the denominator. So x is equal to 2 or negative 2. Oops, I just realized I did that. Hold up. I need to do that here. Sorry. 2, x minus 1, x plus 1, x minus 2, x plus 2. Okay, so again, this one's the easy one. I'm just going to plug in 0. 2 times 0 squared minus 2 over. This is for the y-intercept, sorry. 0 squared minus 4. It's going to be negative 2 over 4, or, negative 4, or 1 over 2. So my y-intercept is at 0, 1/2. Okay, my y-intercepts, remember, I'm just going to look at that numerator and set it equal to 0. So then my x-intercepts are going to be at 1 and negative 1. Okay, but again, we want to write this as points. So 1, 0, negative 1, 0. Okay, so here's my x-intercepts. Here's my y-intercepts. I have some asymptotes from here that are problems for me. Okay, horizontal asymptotes. So if they're equal, if m is equal to n, I'm going to look at the leading coefficients. In this case, 2 over 1. So I'm going to have a horizontal asymptote at y equals 1. Okay. The other case that you could have is m greater than n, but you're going to learn this either in 1050 or AP. Okay, on what to do on those cases. We're not going to get into those cases today. Okay, so I have a asymptote at y equals 2. Sorry, x equals 2. No, y, correct. Y was right. Okay, so at y equals 2, that's where my asymptote is going to be here. Okay, and again, let's cheat a little bit. Let's go look at that and see what that looks like and see if that makes sense. So I've got 2x squared minus 2, and that's all going to be over x squared minus 4. Oops. Come back down there, please. X squared minus 4. Okay, and if I look and I kind of zoom out a little bit, we said y equals 2. Okay, that kind of makes sense. Let's put a line there and just double check. Y equals 2. And again, it kind of looks like it gets close to that, but never quite touches it. And if I zoom in enough and zoom out enough, or zoom out then zoom in enough, that's what it'll look like. Okay, so I've got that asymptote. From my previous ones, I saw that again. I'm going to have a horizontal or vertical asymptotes here and here at 2. Sorry, I'm going to have those x-intercepts at -1, +1, and then I've got it crossing at 1/2. Okay, so it kind of looks like it should do something like this. Okay, so for my sine array, again, I've got interesting things happening at -2, -1, +1, and +2. So I'm going to do negative, 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 positive, negative, 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 or sorry, positive, positive. Again, just get this nice stair-step pattern. Negative, negative, positive, positive, positive. And this is going to be my last one. We're always going to have one less than the number of columns. Okay, so out here, I'm going to have positive. Here, it's going to be negative. Here, positive. Here, negative. Here, positive. So out past -2, I'm going to be positive the whole time. Okay, that makes sense. Between -2 and -1, I'm going to be negative. Okay. Between -1 and +1, I'm going to be positive. Okay. Between 1 and 2, I'm going to be negative again. That makes sense. Gotta go back down. And then in the outside, I'm going to be positive again. Okay, so again, good way to check these is always use your calculator. Okay, but that's the steps. That's the steps on all these. Okay, and really that's all you need to do. The one exception is when we have a whole. Okay, so we're not going to do this case. Okay, again, we're not going to do the case where it's bigger. What that's going to produce, though, let me just show you kind of like what that's going to look like because it's kind of funky. Assuming nothing cancels there, which it shouldn't. X squared minus 2x minus 3. We're going to divide all of that by x plus 2. Okay, what you see here is we have this horizontal asymptote, or sorry, vertical, but we also have what we call an oblique asymptote. So there's a line going this way. Okay, and we won't get into how we find this today. We won't look at those today, but that's what that produces. So anytime the degree of the numerator is bigger than the degree of the denominator, that's what you get. Okay. Now, last thing we need to look at is what if something cancels? So factoring this out, I'm going to get x plus 3, x minus 3. Write that nicer, sorry. Okay, and I notice that this is going to cancel for me. Okay, what's going to happen is now I really only have that problem at x equals -3 from what I can see. But from our original equation, don't forget, and this kind of goes back to, it was kind of nice the way the big ideas did this. It was a don't forget, x also can't be +3. Okay, so we're gonna do this the same way, same steps. So again, let's write the simplified one. I'm gonna have an x-intercept at, hold up, do I have an x-intercept? Maybe not. Okay, so let's come back to that. I'm going to have a y-intercept, though, if I plug 0 in for x. I'm going to have a y-intercept at 1/3. There's 1 over 0 plus 3. So my y-intercept is going to be at 0, 1/3. Okay, again, x-intercepts, we're kind of, jury's out for right now. Horizontal asymptotes, bigger, smaller, or smaller on the top in the numerator. So we're going to have one at y equals 0. Okay, and let's write down what we know so far, or put on our graph what we know so far. So we have some sort of asymptote here. We have an asymptote, again, at -3. It's that +3 that we need to look at. So let's cheat a little bit here and go and see what this looks like. So we're going to do, and we're going to put the original equation in here. So x minus 3 divided by x squared minus 9. Okay, so kind of cheating here. It looks like we only have that one horizontal asymptote. So the question is, what's happening at 3? Well, let's put a table. And let's see what's happening at 3. 3 is undefined. So it's still a problem for me, but it looks like, scrolling in a little bit, it looks like 3 is okay. But what we're going to find is that it's not really okay. Because at 3, it's undefined. Okay, so let's draw this out. Let's do our sine array, because we said, okay, we don't really have one over here. So an interesting number is at -3. And that's it. Nothing else. So negative, positive. So it's going to be, I'm looking at my graph. That should be what I have, right? Negative and then positive. So I'm down here. And then I'm up here. Okay, but again, something's funky about 3. So at 3, we have what we call a hole. So at 3, I have a hole. Okay, we represent holes just by drawing a little circle there. Hey, don't forget, at this spot was a problem in our original equation. Okay, so that's how we represent anything that gets canceled out. Going back, got canceled out. Anything that gets canceled out is going to be represented as a hole. It's not going to be represented on our sine array. It's not going to be a problem for us. It's just going to be a hole. Okay, so this is my graph. Done. Okay, so again, make sure you're getting your work done. Next time we will start looking at trig and getting ready for that. If you're at home, make sure you're trying to get at least 3 to 5 colors, pens, markers, highlighters, whatever works best for you, color pencils, because it's going to make the trig unit a lot easier for you. Please let me know if you have any questions, and I will see you guys next time.